Chapter 7, we'll be getting into polynomials. This is kind of a core concept when we get into algebra, because pretty soon we'll be factoring polynomials. We'll be working with quadratics, and those are things that we're going to use on all throughout high school. So to start off, we're just dealing with our very first thing in polynomials called monomials. And today we're going to specifically be talking about multiplying monomials. So first off, a monomial is simply a number, a variable, or the product of both. So for example, a number could be anything. It could be 3, could be -4, it could be even a fraction, 3/4. Okay, just basically any real number. It could also be a variable. For example, x, h, or the product of both, which would be 3x, y, or 3/5 hb. Okay, anything with the product of a number and a variable. This would not include division of the two. If you notice, this 3/4 looks like division, but it's a number, right? I could write that as 0.75. But if I would have something in this case like 3/x, that is not a monomial, because it is not the product of both. It is the division of both, and that's not a monomial. So moving on, some of these are called constants. It's really just a monomial that's a real number. So a constant is something that doesn't change. Well, all of our numbers don't change. A 3 is just a 3. An 8 is an 8. A -7/2 is a -7/2, right? Variables are things that change. And so constants are just our specific numbers, our real numbers. Let's just look at a few examples to determine whether an expression is a monomial or not. And we'll talk through why it is and why it isn't. If you take a look at the first one, as you notice, there is a subtraction symbol here. Okay? If you look to the last slide, a monomial is a number, a variable, or the product of the two. It says nothing about the difference. So this would not be a monomial because of the subtraction symbol between the 17 and the C. If you look at number 2, we have an f squared in there. Does that make a difference whether it's a monomial or not? It actually doesn't, because this is the same thing as writing 8 times f times g. Well, it's numbers, variables, and the product of both. So yes, that would be a monomial. Looking at 3, that was an example we already did on the front. So yes, that would be a monomial. It's just a number. And 4, kind of like the example we did on the front again, this would not be a monomial because it's not the product of two. If you notice, there is division in there. It's not the product of a number and a variable. So hopefully we got down determining whether it's a monomial or not. It's basically just kind of like one term of the polynomial is what you'll eventually find out. So it's a number, variable, or the product of both. We're going to look at a few exponent rules with our monomials today. The first we'll talk about is the product of powers. So basically, when you multiply a power with the same base. Then we'll talk about a power of a power. Okay, when we take a number to a power and then we exponent on that as well. And then the power of a product, if you can tell, the product of AB, and we take all that to one power. So just a quick walkthrough before we go through it into a little more depth. When we do a product of powers, and they're to the same base, as you notice here, these are both to the base of A. What I can do with their exponents are add them in the end. Okay, it might not make a lot of sense right now, but we're going to go into that a little more in depth here. For a power of a power, what ends up happening is I take the base and I multiply the two powers. So I took b to the m power, and that was to the nth power. So really it's b to the m times n power. And we'll get into that more in depth here in a second. And the power of a product, it's kind of like your distribution property. So for example, when we had something like this, 3 times x plus 2, remember how we distributed the 3 and got 3x plus 6, because 3 times x and 3 times 2. The same thing kind of works for the power of a product. We basically just distribute the m power. So I would take a to the m times b to the m. So let's get into the product of powers a little more in depth first. So here's an example using a variable with an exponent to a number. So I have a to the third power times a to the fourth. Well, I could expand both those out. If you look at a to the third, that's the same thing as a times a times a. And if you notice, we have multiplication in between the a to the third and a to the fourth. And a to the fourth is expanded out as a times a times a times a. So essentially, I'm taking a times itself 7 times for an answer of a to the 7th. So if you look, to get that, all I really did was take a to the 3 plus 4 power for a to the 7th. So hopefully that makes a little more sense on why that works, why I can just add their exponents. If you notice though, I have the exact same base of a. Exact same base of a. So if I had something that said a to the third times b to the fourth, I cannot add those. I can't say ab to the 7th power. That doesn't work. This is just, that'd be the final answer for that. I can't do anything with that. That's already simplified. So they have to be to the same base. Let's take a look at a few examples here. So my first one, I have r to the 4th power and negative 12r to the 7th, and we're multiplying them. Really, this is just multiplication all the way through. If you notice, I really just have r to the 4th times negative 12. I'll just put the negative 12 in parentheses so you can see it a little better. Times r to the 7th. And if we remember, multiplication is associative, so I can multiply anything I want to before anything else. So what I might do is I might combine my r's together. I'm going to multiply those two first. And if we take a look at our property, I just add their exponents, right? So r to the 4th times r to the 7th is really r to the 11th. And there's nothing to multiply with that negative 12, so we always put our constant out front to give it our coefficient. And that would be our final answer right there. Negative 12r to the 11th. So basically just multiplying your variables together that have the same base. In this case, they both had a base of r, so I could just add their exponents. And the negative 12 just gets brought out front. Looking over at the next one, now we have a couple numbers to deal with. I got a 6 and a 5, so I can combine those first. This is really just 6 times c times d to the 5th times 5 times c to the 5th times d to the 2nd. So if I wanted to rewrite this, I could really write 6 times 5 to combine my two numbers first. Then I could write c times c to the 5th and times d to the 5th times d to the 2nd. Right? Because by the commutative and associative properties, I can go ahead and just switch those around. And then just follow your rules. 6 times 5 gives me 30. C times c to the 5th, that's really c to the 6th. Because if you think about it, this is really c to the 1st power. And if I would expand my c to the 5th out, it'd be c times itself 5 times. So that'd be a total of 6 c's. So c to the 6th. And then we take our d to the 5th and d to the 2nd. We add their exponents for d to the 7th. And there's nothing else I can do with that to simplify. So that would be my answer. So remember, our product of powers, they have to be to the same base. Looking back up at our a's here again, remember, they're both to the base of a, so I could just add their exponents. But looking at the example I had up top, in the top left, a and b are different bases, so I cannot do anything with that. So you have to leave them. Okay, let's move on. How about a power of a power? Well, if we think about it, this b to the 3rd is just getting multiplied by itself 5 times. Okay, and so I could write that out. I could say b to the 3rd times b to the 3rd times b to the 3rd. Okay, getting kind of repetitive, I know, but sometimes it helps just to visualize it. And I could break that down even further. B to the 3rd is really b times b times b right? I go to the next one, b times b times b, and this goes so on and so forth. In the end, I end up getting 15 total b's multiplied by itself. So let's just do our shortcut. Whenever I have a power to a power, I just multiply. So it's really b to the 3 times 5 power, which gives us b to the 15. So there's our shortcut with that. And hopefully this expanded out version right here helps us understand why that works. Once again, let's do a few examples. So first example, I'm taking 3 to the 2nd power, which I'll take to the 3rd power, and finally to the 2nd power. Well, the nice part about our shortcut is anytime you take a power to a power, you can just multiply. So really, I'm just taking 3 to the 2nd times 3 times 2nd powers to give us a total of 3 to the, well, 2 times 3 is 6, and 6 times 2 gives us 12. So 3 to the 12th power. I could simplify that even more by actually taking 3 to the 12th power on my calculator. It's going to give us a pretty big number, so let's just leave it as 3 to the 12th power. It looks much nicer that way. Same thing with our next example. All I did was use a variable instead of a number. Same type of thing though. I would take 5 times 2, which is 10, and take that times 3 to give us 30. So it would be p to the 30th power. So power to a power, they simply get multiplied. Our last one we introduced was a power of a product. And if you remember, this is very similar to the distributive property, right? So if I look at my example here, I have a times b to the 2nd, and I'm taking all of that to the 3rd power. So what's really happening is I'm just distributing this 3rd power to each of them. So I'm going to take a to the 3rd, and I'll also take b to the 2nd to the 3rd power. And if you remember, that was just what we covered, is a power to a power, that's b to the 2nd to the 3rd, so we end up multiplying those two. So I still have a to the 3rd, but then it'll be b to the 6th, right? 2 times 3 gives us 6. So essentially I'm just distributing that power. So let's take a look at our example here. I'm going to write this just a little bit bigger. Negative 2 times x times y to the 3rd, all to the 5th power. And just like I said, just distributing this power to each part of that monomial. So I'm going to take negative 2 to the 5th. This is important that we have this negative 2 in parentheses, especially if you're going to type that into a calculator, because that will change the answer if our exponent is even. I will take x to the 5th, and I will take y to the 3rd to the 5th. I'm sure some of you can skip some of these steps that I'm showing right here, but I just want everybody to be able to see this. Well, if I take negative 2 times itself 5 times, I'm going to get a negative answer, right? An odd number of negative factors gives me a negative answer. And 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 gives me 32. So I have a negative 32, x to the 5th, and like we said, a power to a power, I multiply. So 3 times 5 gives me y to the 15th. So there's my final answer. I simplified that monomial into negative 32, x to the 5th, y to the 15th. So let's use some of these properties to be able to do some different situations. It asks me, express the volume of a cube with side length 5xyz as a monomial. Okay. Some people might be able to come up with this right away if you know the formula for a volume of a cube. Some people might need to visualize this. So let's go ahead and draw a picture of a cube here. And it tells us that the side length is 5xyz. Well, in a cube, it doesn't state it's a rectangular prism. It states it's a cube. In a cube, all sides are the same. So all sides are the same. Every side would be 5xyz. z. And hopefully by this time, we've known that the volume of a cube or a rectangular prism is the length times the width times the height, right? The length times the width would fill up the area of the bottom here, times the height would fill up the rest of my cube going up. So it's really length times width times height. And they're all the same, aren't they? So I could write 5xyz times 5xyz times 5xyz. But to simplify that, I could just say 5xyz to the third power, right? Because I'm multiplying it by itself 3 times. And that would be our product of powers property. Like I said, it's very similar to the distributive property. We're going to go ahead and distribute that third power to all of our numbers and variables in there. So 5 to the third gives me 125. X to the third, y to the third, z to the third. In this case, there is no units. It doesn't say inches or centimeters. So it would be units cubed for the measurement, right? If it was inches, it'd be inches cubed, centimeters, centimeters cubed, and so on. What about the circle? To express the area of a circle as a monomial. Well, we need to know how to find the area of a circle. Hopefully, you got this down. Otherwise, you might have to reference back to your book, take a look on it online. But if you remember, an area of a circle is area equals pi r squared, right? Pi times a radius squared. And if we look, it gave us our radius right here, correct? Remember, radius is half the distance across the circle there, the center. So from the center to any side of the circle. And all we're going to do is plug that in for r. So area equals pi, better put this in parentheses, 2xy to the second. Same thing as last problem. I'm going to distribute my second power here. And I end up with pi times 2 to the second, which is 4, x to the second, y to the, well, 2 times 2, right? Power to a power, y to the fourth. Let's clean that up a little bit. Let's bring our 4 out front. The pi is just a variable, right? It represents a number, 3.14159, so on and so forth. So bring the 4 out, pi x squared y to the fourth. And once again, units. And this time, it's area, not volume, so units squared. So there's kind of using it in a geometrical sense with our monomials. Last one. I want you to try this one on your own. Okay, so maybe pause the video, give this a shot on your own. If you can solve this, I think you're going to be able to solve almost all of our monomials that we're multiplying. Okay, and then when you think you're ready, go ahead and hit play, and I'll walk through it here with you. So really, you still follow your PEMDAS, right? You look at your parentheses, go to your exponents, work inside out of your parentheses, so on and so forth. So I'm looking, I'm probably just going to work with this part of it first, and then I'll go to the second part. So I'm going to work inside out. First I'm going to distribute this second power here. So I'll go ahead and do that. So I got 8 squared, which I guess I could replace that with 64. I got g to the third squared. So remember, power to a power we multiply, so 3 times 2. So that would be 6th. Then h to the 4 times 2, right? 4, fourth power to the second power, so 8. And if you notice, I still have this square out here. So I can get rid of the brackets. I could put it in parentheses, or I could leave the brackets. It does not matter. But just remember that you still have to square all that. And then I'll bring down the rest of my part. I suppose I could distribute that as well, all in one step. So it looks like we got 2 to the 4th. I'll just write 2 to the 4th for now. G to the 4th and h to the 5th to the 4th. Remember, power to a power, 5 times 4. So lastly, I still got to distribute this second power here. So we will have to take 64 to the second power which gives us 4,096, and g to the second, or g to the 6th to the second, so g to the 12th, remember we're just multiplying, and distribute that to the 8, so h to the 16th. And this one is already finished out for us, right? We could just take 2 to the 4th, which gives us 16. There's still one step left in here. If you notice, I have two numbers. I got variables with g, and I also have variables with h to a power. So we can go ahead and combine kind of our like terms there in a way, I guess. So we take 4,096 times 16. There's 65,536. We take our g to the 12th times g to the 4th. Remember, we're multiplying powers to the same base, right? So it's really g to the 16th. I can just add those exponents. And lastly, same thing with the h's. H to the 16th times h to the 10th gives me h to the 26th. And then I would be done. So it just takes a few steps. Just don't get some of those exponents lost. It's easy to get them lost when you're dealing with a lot of those exponents in there. So take it step by step. That would be your simplified form. Okay, looking at today's assignment, if you want to get a head start on it, that'd be great. If not, come to class tomorrow with any questions that you're ready for, and we will take a look at this together, get going on it, and I'll be walking around and helping you out with this assignment. Have a great night.